Last time we were talking about what makes protons different, and we had ended with this example where we had identified that the two methyl groups are chemically different. The purple hydrogen and the yellow hydrogen are chemically different, but we were talking about A and B and whether or not they're different. So the question to ask is there any symmetry operation that could make A and B interchange and have them experience exactly the same things? So, for example, is the board or the page, is that a mirror plane for this molecule? Is what's above the plane the same as what's below the plane? Looks okay till you get to the alpha carbon, and the OH isn't the same as the hydrogen that's below the page. Similarly, HA is on the same side of the page as the OH group versus HB, which is on opposite side of the page as the OH group. So they experience different environments. Now, you could say, haha, let's just rotate around that carbon-carbon bond and we can make it so that HA is on the opposite side of the molecule as the OH group. Fine, but when you do that, now HB is on the same side as the OH group. No matter what you do, HA and HB can never experience the same environment. And this is a general feature of chiral molecules. In chiral molecules, CH2 protons are chemically different. That's important because that means they might have different chemical shifts. We have a word to describe a situation in which you have CH2 protons that are chemically different in a chiral molecule. The word for that is diastereotopic. Topic is for shape. Diastereo comes from the same word we use for diastereomer. A and B, so the thought experiment is this. If you were to replace A with something that's not hydrogen, something you could tell the difference between, something you could distinguish from HB, take a look at that molecule and then do the same thing with HB, those two possibilities are diastereomers of each other. And what that means is that HA and HB are in diastereomeric environments that are not the same. The origin of this term is a little bit confusing. You don't need to understand it at this stage at any other level than to be able to accept that in chiral molecules, two groups attached to the same carbon are not identical to each other. All right? That'll come up again and again when you take 353. Dr. Bronson will really push you on that, and you'll need to remember that as you're interpreting NMR spectra. Any other questions about identity of protons, where they're chemically identical versus distinct? Recalling that we care about that because distinct protons in distinct environments have different chemical shifts, which we talked about last time. All right. So far we've learned we can tell something about the number of different kinds of protons in a molecule from an NMR spectrum. We've also been able to tell a little bit about what functional groups might be nearby, but so far we have nothing for connectivity, no way of figuring out what each proton is next to. So before we do that, we need to maybe review just a little bit of probability. Hannah, what do you think? Should we go? No, it did not work for you. Best just to. No, that's okay. It was bad. Yeah, so there's this extended analogy about Anakin Skywalker, Count Dooku, and Chancellor Palpatine flipping coins. Okay. Well, now I have to, even though it's stupid. Do it. Do it, right? Okay, so we imagine ourselves on the observation deck in General Grievous's vessel during the Battle of Coruscant, and Chancellor Palpatine has been kidnapped, held hostage by Count Dooku. Hannah's leaving because it's so terrible. And Anakin has, they have the battle, and Anakin disarms or dishands Count Dooku, so to speak, and he's waiting there with his lightsabers, trying to decide whether or not to kill Count Dooku. Chancellor Palpatine says, "Do it." And Anakin says, "I really shouldn't. What should I do?" And at that point, the Toydarian Watto, who had previously enslaved Anakin, wanders in, and he says, "I just happen to have a chance," not cube, in this case it would be a coin. And Anakin says, "That sounds great. I'll flip the coin. Heads, I go to the dark side, and tails, I stay on the light side," or something like that. So, and Palpatine says, "That sounds great." So Anakin starts flipping coins and starts tallying up how many times he sees heads versus tails. He decides after the first few flips, heads is Sith and tails is Jedi. First few flips are heads, and Palpatine's getting excited, and he says, "Good, Anakin." But then Anakin says, "Well, no, we need to actually make sure this is reproducible." And after about an hour or more, you've come up to the conclusion that it's basically 50-50. And so both Anakin and Palpatine are totally flummoxed. Not sure what to do, and so Palpatine suggests that Dooku flip a coin, to which Dooku says, "I don't have any hands anymore." But then Palpatine says, "Well, you're a Sith Lord, aren't you? Can't you flip the coin with the Force?" So Dooku starts to do that, and now you've got two people flipping coins to try to determine whether we should be Siths or Jedis. And so there are various possibilities when two people are flipping a coin. We've got Anakin and Count Dooku, and Anakin could flip heads and Dooku could flip heads, or one could flip heads and the other could flip tails. Of course, there are two different ways to do that. Possibly Count Dooku could flip heads and Anakin could flip tails. And then there'd be the possibility where they both flip tails. All right? And we can't really distinguish between these two outcomes. They both say the same thing. So if we were to do this, and again, they take about another hour at this, and at that point, everybody's sort of hanging out, wondering, what do we do outside? They're starting to play soccer or something because they're bored. The clones are, anyway. Sorry, this is getting. Yeah. So at about another hour later, they observe that there's about twice as many times where they see one heads and one tails as there are times where they see either two heads or two tails. And I don't know about the spacing here. It's kind of messy, whatever. But in terms of outcomes, you've sort of got a 25 to 50 to 25 ratio of possibilities. And the reason that the central one is twice as big as the ones on either end is that you have two different ways of getting that outcome. So at this stage, it's still a tie with the majority saying, we don't know what to do. So they decide to go recruit some others. At that point, the fans resurrect Darth Maul, and he comes in and they start flipping. And there's never any resolution because the highest peak is always the one at 50%. And therefore the war is over because the Sith Lords are eternally flipping coins and everybody else goes about their business. The end, right? End of saga. I feel like it precludes a better story. I don't know. There you go. That was, oh my goodness, 10 minutes. So, so probability in this way is important to us because it's related to how a proton that we might be interested in, proton A, how it is influenced by the presence of another nearby proton. All right, so proton A and proton B are 3 bonds apart from each other. We'll call this the alpha carbon and this the beta carbon. Proton B is adjacent to proton A. We're going to be focusing on what proton A experiences when it's in an external magnetic field. Now, last time we said that the field that proton A experiences, I'll just define that, the field that proton A experiences is equal to the external magnetic field and then the influence of the induced magnetic field. This is what happens when the external magnetic field causes electrons in the molecule to move around in a way that generates an induced magnetic field. Sometimes that induced magnetic field, most of the time it opposes the external magnetic field, but in the case of benzene, it can reinforce it. So I'm just going to make a note here that this could be positive or negative, depending on the situation. We'll just use a plus sign, and then we'll say this number can be positive or negative. All right, and so far that's where we got the energy gap between with versus against the field, and that's where we got the frequency, radio frequency to promote spin flipping, and that's where we got chemical shift from. And that's a number that we can measure. And that was considering just a proton by itself without any other protons nearby. So we would see a peak at chemical shift, and there would just be one. 100% of molecules with HA in them would be in this situation. Okay? However, once we introduce nearby protons, we increase the number of possibilities for the field that proton A can experience, because proton B is itself a magnet. Proton B has a magnetic field. It has an angular momentum. It has spin. And in any given molecule, the spin of proton B can be either with the magnetic field, we'll call that plus little b for proton B, or it can be against the magnetic field, we'll call that minus little b for proton B. Okay? And the probability of that is 50-50. That is, in 50% of molecules, proton B is aligned with the field, and in the other 50%, it's aligned against the field. And this has to do with the fact that the energy gap is so low that the population's still basically 50-50. Okay, you with me so far? You accept the fact that B's got 2 possibilities. So A is the observer and B is the coin flipper. And so now, instead of there just being one situation for A, there are 2 situations for A that A can experience. 2 possibilities. Of course, each proton A only experiences one of these 2 possibilities, but we've got gazillions of molecules in solution, and so each of them can experience one of these 2 situations with equal probability. Situation 1 is that proton A sees proton B with spin aligned with the external magnetic field. The other situation is proton A sees proton B with spin aligned against the magnetic field. All right, so in situation 1, the field that B experiences is still the external field plus the effect of the induced magnetic field, but now it's going to be plus the impact of the field from B being aligned with the external magnetic field. I will say, though, that this number is very small. Okay? Whereas for situation 2, the observed, the field that proton A experiences is going to be what we did before, but now subtracting the field from B because it's aligned against the magnetic field. All right? So BE from situation 1 is a bigger or stronger field or larger magnitude, whereas the field in situation 2 is of smaller magnitude, right? Because in situation 1, the external field is reinforced by B. In situation 2, the external field is reduced by proton B. Two different situations, and probability is equal, 50-50. How will this change in field affect chemical shift? Well, what we should observe in situation 1 is the chemical shift of A. In situation, we observe a chemical shift in situation 1, the natural chemical shift of A plus some change in chemical shift that comes from the presence of that field due to B. And then in situation 2, we're going to observe the chemical shift of A minus some difference that comes from the field being aligned, the external magnetic field and the field from proton B being aligned against each other. Okay? So situation 1, we move to higher chemical shift just a little bit. Situation 2, we move to a little bit lower chemical shift. What this will do, because 50% of our molecules are in situation 1 and 50% are in situation 2, what we're going to observe in an NMR spectrum, if this is chemical shift on the x-axis, and on the y-axis we have something that's related to number of observations, but averaged over a whole population, it's more like absorbance. So we'll just put maybe I don't know. We expect to see 2 peaks for proton A in a 1-to-1 ratio, and they should be separated by a distance that's related to I guess to be consistent with the way we've been writing things, they are separated by a distance that's related to the influence of that field. Okay? We expect to see 2 peaks present in a 1-to-1 or 50-50 ratio in terms of their intensity. And they should be separated by an amount that comes from the influence of that nearby proton. Okay, that's kind of a lot, so let's pause for questions, because this is tough to get. Yeah?
So are you meaning that the change in chemical shift, the distance between those two bands or whatever, is going to basically be the range from the large magnitude to the small magnitude?
Yes. Yeah, the distance between these two bands is going to be related to the change from situation, oops, I'm erasing stuff, situation 1 to situation 2. All right? This distance we could measure. I'm troubled by the fact that I put delta up here, and that now the distance had to be 2 times delta. We're going to... it turns out that this amount in terms of actual chemical shift is going to be in the tenths to hundredths place. And because of that, we're going to convert this back into frequency using the equation that I showed you last time. Fortunately, the computer program does this for you. You don't have to do it ever. but you convert back into frequency. That's difference in frequency between the two peaks. We call that difference in frequency between the two peaks a coupling constant. It's because the fact that proton B influences what proton A experiences is called coupling. All right? And the coupling constant, we give a symbol J. I don't know why they chose that symbol. We use the subscript A and B to say that it's the coupling between A and B. Sometimes people will put a superscript 3 there to indicate that A and B are 3 bonds apart. That's beyond the scope of what we want to worry about. Coupling constants vary all over from 0 to like 15 hertz. Remember, the coupling constant is in frequency terms, in units of hertz now. But most commonly, we see that coupling constant equals around 7 hertz on average. Okay? One really interesting thing is, and this is the signal I should point out, this is what we observe for proton A. We're not even talking about what proton B sees. Those two peaks don't represent A and B. They represent proton A in 2 different situations influenced by the presence of B, right? And I forgot what I was going to say after that. So, other questions? Yeah?
What does a larger coupling constant mean about, or what does that translate to?
What does larger coupling constant translate to? A lot of things can influence coupling constant. This is not important really for the class, but actually if you look at A and B, they're adjacent to each other. Orbitals appear to be involved in the coupling process because coupling constants are largest when protons are anti to each other. And they are next largest when protons are eclipsed to each other. That is, when the bonds are aligned and the orbitals are aligned. When HA and HB are at around 90 degrees, coupling constant becomes very small. That's neither here nor there. I don't think it'll be that important for the class, but that's practically what people observe. What else? Okay. So, folks in the chat are interested in examples of how you might use this, and we'll get to that, I promise. George asked, how in the world did people figure this out? It was physicists who didn't have anything better to do. And actually, at the beginning, it was kind of viewed as an esoteric technique, but actually it's a godsend, honestly, because fortunately, organic molecules have lots of carbon and hydrogen in them, and those are the very things we can see pretty easily by NMR. So, hand of God, happenstance, who knows? You can believe whatever you want, but we are really, really fortunate. I don't believe it's happenstance, I'll just say that. Where are we? Keep getting lost. Oh, Hannah knows what's coming next, so she's like, you could look in your notes. Okay, thank you. So some have asked, what if there were 2 protons nearby instead of just 1? Okay, so let's still be focused on HA. Everybody else will be lonely. What did they ever do to deserve our lack of interest? HA, HB, and HC. And we're going to say in this example that HB and HC are chemically identical. They're not diastereotopic, they're identical to each other. And therefore, the coupling constant between A and B is going to be equal to the coupling constant between A and C. Both of these, B and C, will influence A in the same way. Okay. So let's just consider the various possibilities that A can experience, the various situations that A can experience. Now, I'm not going to go back and do all of this thing with adding B's together because we don't need to. All we need to do, we know that the spin of B influences the chemical shift that we observe for A. So we just need to consider the possibilities for the spins of B and C. B can have either upspin or downspin, and you've got a 50% probability of either of those outcomes, meaning B can only be one of those in any given molecule, but we've got gazillions of molecules, and so if you were to investigate each one, flipping the coin basically to infinity, you would get a 50-50 ratio. Similarly, HC can be either with the external field or against the external field, and again with 50-50 probability. This is just exactly like Anakin and Dooku now both flipping coins and not cheating, which, you know, given their later history is dubious, but so was the whole analogy. Let's consider the possibilities then. B and C could both be up. B and C could both be down against the field, and one could be up and the other down, whereas B could be down and C could be up. And these two outcomes are the same as far as A is concerned. A can't tell whether A is up and C is B. A can't tell whether B is up and C is down versus B is down and C is up. So we have three situations, 1, 2, and 3. Each of these individual possibilities, you can come up with the probability by multiplying 50% by 50%. It's 25%. Each of these outcomes is itself 25%, but they are the same, so that's 50% overall. And then having both spins down is another 25%. So those are the probabilities, meaning if we observe all the molecules in solution, we're going to encounter proton A in these three different situations. Where B reinforces the external magnetic field, we're going to have, in situation 1, we're going to have a larger field that's experienced. That's going to lead to larger energy gap and larger frequency, and therefore larger chemical shift. In situation 2, the two should cancel each other out, actually, with versus against, and we're just going to see the normal regular field and therefore chemical shift that we would expect. And then in situation 3, we'll see a smaller, A will experience a smaller field and therefore a smaller chemical shift. Yeah?
Just to clarify, so the chemical shift for the one where they cancel out, that's going to be the same as if A were on its own?
That's going to be, yeah, to repeat the question, great, good question. The one in the middle, the 50% option, where the influence of spins B and C cancel each other out, is going to be the one we would see if A were just on its own, if we could somehow turn off the coupling between A and the neighboring protons. Okay. So, based on this, if we were to, again, look at an NMR spectrum, we would see a peak for A, and it would be split into the following pattern. In roughly a 1 to 2 to 1 ratio. Technically, it's a 1 to 2 to 1 peak area ratio, but in most NMR experiments, the lines are pretty thin, and peak height is about the same as peak area, so you can use peak height as a way to monitor these ratios. Now, before I said that the coupling constant between A and B and between A and C is identical, let's just say it's 7 Hertz, and that's important. That's actually why we observe this 1 to 2 to 1 pattern. The 1 to 2 to 1 pattern we're going to call a triplet, whereas the 1 to 1 pattern we're going to call a doublet. All right. Yeah.
How does proton A's own spin figure into figuring this out?
Good question. How does proton A's own spin figure into this? When you're observing proton A and you're shooting radio frequency radiation at proton A, its spin doesn't matter in the sense that you're causing it to flip and you're disrupting the population. That is a hand-wavy answer. The real answer to that question is I'm not sure. But when you observe A, you don't see anything about A's spin, because what you're measuring is the ability of A to spin flip at that frequency. Other questions? Incidentally, if we decided to be protons B or C, they're identical, and they'd show up at the same chemical shift, what would the peak for B and C look like? It's adjacent to only A. Doublet, right? And if proton A were adjacent to no protons, it would be a singlet. Okay, conceptually we can think about the triplet in a slightly different way. You can think about imagining what the chemical shift of proton A is. I'm going to sort of keep this lined up. Let's say that we turn off the coupling between A and B and the coupling between A and C. So for HA, we just see this one peak. Then, at this stage, we're going to turn on the coupling between A and B, which equals 7 hertz. That's going to create the situation where A is split into a doublet, a 1-to-1 doublet. Then, subsequently, we're going to turn on the coupling between A and C, which also equals 7 hertz. And that's going to split the peak on the left by the 7 hertz distance. And it's also going to split the peak on the right into 2 equal peaks that are 7 hertz apart. And it's just going to happen that the peak here that 2 peaks will coincide in the middle, overlap with each other, and that's where we get the double intensity from. So 2 different sort of related ways to think about where a triplet comes from. And it's often useful to reason through this by thinking about turning on successive couplings. Actually, this picture of where we get the 1 to 2 to 1 triplet versus the 1 to 1 doublet allows us to use a mnemonic device for the kinds of intensities and number of peaks we should see depending on the number of adjacent protons. And we can do some predictions. So the mnemonic device is actually Pascal's triangle, which is, I think, coefficients for x plus 1 raised to the nth power, where n is 0 to whatever integer you want. Except in this case, n is going to equal the number of protons. If there are 0 protons, you're going to see a single peak. If there is 1 adjacent proton, you're going to see 2 peaks with relative intensity 1 to 1. The number of entries in this row will indicate the number of peaks. The actual value of that number will indicate the relative intensity of those peaks. When n equals 2, you've got 1 to 2 to 1. When n equals 3 adjacent protons, that's 1 to 3 to 3 to 1. This is doublet, triplet, quartet. Being adjacent to 1 proton, 2 protons, 3 protons. Most commonly, being adjacent to 2 might be having a CH2 near you. Being adjacent to 3 might be having a methyl group near you. There are other situations that you can envision. And all you have to do is continue to fill out the entries in the Pascal triangle to see the kinds of distribution of peaks you can expect to see. Though the more nearby protons you have, the more that single peak is going to be split into smaller peaks, and the harder it becomes to interpret. Usually, we're not that good at interpreting things beyond about 3 or 4 nearby protons. Okay, questions so far? Yeah.
So for a quintet, where it's 4,
Uh-huh.
you have 6 that are overlapping.
For a quintet, you have 5 separate peaks, but yeah, if you were to run it down in this way, there would be 6 situations overlapping at that central point.
It doesn't make it any smaller, right? Because you're splitting up one.
You're splitting the one intensity into those 5 different places. So, yeah, the overall height of the peaks actually is going to get smaller for a given single proton. We haven't talked about the fact that peak height is proportional to number of protons represented by a peak. So if you were changing the number of protons, that would, anyway. But yeah, for just a single proton, 50, 50, 25, 50, 25, and so on, the percentages start to get smaller. In particular, these peaks on the outside become much, much smaller. Other questions? So nobody wants to ask the what if about what if A and B are actually different from each other. Too bad, I just did. But I will show you an example of some peaks that are split. Nope, not that one. Did that last time too. Oh, nope, there it was. Erase, 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 don't look. Okay, so here's an NMR spectrum of a molecule. There are 3 different peaks. You might be tempted to say this is 4 peaks, and you're right, but it is for one kind of proton. So you're thinking about closely grouped peaks. And if you zoom in, you see that in terms of peak height, it looks like a 1 to 3 to 3 to 1 ratio, which would make it a quartet. Based on what we know, then, how many protons would be adjacent to the proton represented by this peak? Got to have 3 adjacent protons. Now at this stage, all we know is that the 3 protons are adjacent to the one represented by this peak, and we know that their coupling constants between, we'll call this proton A, and the rest of those 3 adjacent protons, each coupling constant has to be the same. It might be that these 3 adjacent protons are identical. If that were the case, it could be a methyl group. Rather, it would represent that HA is adjacent to a methyl group. But there might be some other situations you can envision with 3 identical protons not on a methyl group.
Sorry,
Though,
how do we decide if they're identical?
huh?
How do we decide if they're identical?
Yeah, the question is, how do you decide if the neighboring protons are identical? You won't get that from looking at HA, but you would get that from looking at the peak that represents those adjacent protons. In this case, I happen to know that this peak here represents those 3 adjacent protons. I happen to know that because of some peak area information we haven't talked about yet. So that the fact that I'm seeing 3 protons all represented by the same peak tells me that they are identical to each other. Another interesting feature is the fact that if this represents the 3 protons and this represents 2, this is sort of peak height or peak area, and it's proportional to number of protons, 2 and 2 and 3. It's interesting that the peak that represents 3 protons is a triplet, which would mean it's adjacent to 2. So you get complementary information, right? This one is a CH2 group adjacent to a CH3, and this one is the CH3 group adjacent to the CH2. So thankfully, NMR is kind of like Sudoku. You've got probably more than enough information to solve what the problem is, and you can actually find confirmatory information as you continue on in the process. We'll do some more examples of that. Any sort of questions so far about what we're looking at? Yeah.
Yeah, you mentioned there might be another situation in which we have three identical protons that's not a methyl group. What would be a case in where we did have three?
I can't think of one other than it would have to be something like this,
Okay.
where the molecule is highly symmetric, and that's like probably the only one. So
Okay.
3 adjacent protons, almost always a methyl group. Okay, others? Yeah.
What is the peak that's represented by 29?
What is the peak that's represented by 29? Well, according to, it would look like it has, because of intensity, and we haven't talked about that yet, I'll just tell you 3 protons, 3 protons, 2 protons. It's just a singlet that's not split. So what does that tell you in terms of how many adjacent protons it can have? 0, right? So this could be a methyl group, and likely is, but whatever on Earth X is, there are no protons on it. And that starts to constrain what you can do in terms of the structure. With that information and molecular weight and information in the IR, we actually have enough to solve this structure, but we'll hold off on that. Okay, other questions? Good. All right, so let's deal with the situation where B and C are not in fact identical to each other and therefore don't have the same effect on A. I'll show you an example of that situation. Let's draw this olefin. We'll let the R group be something, but no protons. Okay, well, maybe I should just choose something. I'm struggling, whatever. Okay. We've got 3 protons associated with the alkene. B and C are not identical. C is cis to this ester, B is trans to the ester. Different environments. In fact, B and C are examples of, is another case of diastereotopic protons. Protons on an olefin can be, or on a substituted olefin, on the same carbon of a substituted olefin are diastereotopic. Okay. Meaning that if you replaced one with something versus the other with something else, those two options would be diastereomers. In any case, they are chemically distinct, and this is a situation in which the coupling constant between A and B is not the same as the coupling constant between A and C. And right now we're just focusing on proton A. Now, I happen to know that in olefins, protons that are held trans to each other have kind of a large coupling constant. It ends up being around 15 hertz. Whereas protons that are held cis to each other, sorry, C is the trans one, isn't it? And B is the one that's held cis to proton A, tends to be around 10 hertz. What does this mean? Well, to understand it, we could go through it the way we did with all the various possible options up and down and such. But let's just do it the way we did the triplet here. Let's imagine we can see proton A. This is the chemical shift when we have turned off the JAB and the JAC. Okay, that's just the intrinsic chemical shift of proton A. Now, let's turn on the chemical shift between A and B. And let's just say that this distance is 15 hertz. And as expected, when we turn on coupling between just with just one other proton, it's a doublet, split in 50-50. Now let's turn on, Joshua, isn't somebody going to stop me? We turned on the coupling between A and C there because A is the one that's trans. I'm really, really sorry. That means I need to go back and say it all again. So we started with proton A, turning off the coupling constants with the protons B and C. Then we turned on the coupling constant between A and C, which we said was 15 hertz, and that's this distance. Then, in a second step, we will turn on the coupling between A and B, which we said was just 10 hertz. So starting from the peak on the left, I split that by 10 hertz into a 1-to-1 doublet. And then with the peak on the right, I split that by 10 hertz into another 1-to-1 doublet. The only difference between what we just did here and what we did before with the triplet is in the triplet, the two successive coupling constants were equal, so the central peaks overlapped. But here, when they're different, they don't overlap anymore. You don't see the triplet pattern. Instead, you see something that we're going to call a doublet of doublets. Okay? And they will be present in a 1-to-1-to-1-to-1 ratio. And that is because the coupling constant between A and C is different from the coupling constant between A and B. Someone in the first hour asked, what if you turned on the coupling between A and B first? You can go ahead and try that. Split this peak by 10 hertz and then split those two peaks by 15. You get exactly the same answer. All right. Questions? Another situation besides olefin where you might see this kind of thing is actually going back to our alcohol, you can see this in a situation where you have a proton in a chiral molecule where B and C are diastereotopic. Then you're going to see coupling independently between HA and HB, and then coupling between HA and HC. All right. A couple other things that came up. Go ahead, Sen.
When you say turn on, like the JC or turn on JC, how do you manipulate that?
So can you do this in the lab where you turn off one coupling versus another? Yes. I don't understand how. So we're doing it conceptually. We're just saying, what would you expect to see? We're trying to derive where the observed pattern comes from, because this is the pattern we observe. And we're saying it comes from two different coupling constants.
Okay.
Yep. Others? All right, a couple other questions that came up in the first hour, and then it's gone. Oh, what about B and C? What do B and C observe? Well, let's go back up to where B and C are identical with each other. Protons that are chemically identical to each other don't couple. J, B, C equals 0. There is no splitting of B by C or of C by B. I'm not sure about the mechanism of that, but that's just what we observe. However, B and C that are different can couple with each other. So in this situation, because HB does not equal HC, it's possible for the coupling between those two to not equal 0. And in fact, in this case, being on the same carbon, only separated by 2 bonds, in an olefin actually has, that coupling constant is closer to, I think, 5 hertz. It's in your text. It might be smaller or larger than that, but that's about where it is. And I guess that's where we'll have to leave it for today.